In this short video, I want to talk about rational canonical form for matrices. So we know that every linear transformation T has a unique rational canonical form. But what about matrices? So the idea is we're going to start with an n by n matrix A with entries in F, and we're going to build a linear transformation from it. Then we're going to use the fact that that linear transformation has a unique rational canonical form to make a corresponding statement for the matrix. So A is just going to be our n by n matrix with entries in F. Let's say V is some n-dimensional vector space over F. The big idea here is something we've seen before a number of times, that we're going to define a linear transformation T from V to itself by choosing a basis B for V and setting what does T do to a vector V? It is equal to A times the column vector of coordinates of this vector V with respect to this basis B. So we just choose some basis, and then we're going to define this linear transformation that comes from multiplying by this matrix A. What is the relationship between T and A? Well, the matrix of T with respect to B is A. And now, A is a matrix representation of some linear transformation T. So we start with a matrix, we get a linear transformation. Now the big idea is that T has a unique rational canonical form. That means that there's some basis of V such that the matrix representing T with respect to that basis is in rational canonical form. And what's true about that rational canonical form matrix and this matrix A is there are two matrix representations for the same linear transformation with respect to different bases. That means that those matrices are similar. So this matrix is similar to A because it comes from choosing a different basis of V, but looking at the same linear transformation T. So in this way, the uniqueness for the rational canonical form for T is giving us a uniqueness statement for matrices similar to A in rational canonical form. So the theorem is the matrix of A. The matrix A is similar to a matrix in rational canonical form. So which one? Well, you build this linear transformation, and then you take the rational canonical form of that linear transformation. And we're going to call that matrix the rational canonical form of A, or the rational canonical form for A. And two, this rational canonical form for A is unique because what are the matrices that are similar to A? They're matrices that come from this linear transformation T with respect to different choices of bases. And because there's a unique choice of rational canonical form for T, we also see that there's a unique matrix in rational canonical form that A is similar to. So we know what the invariant factors of an F bracket X module are. We know what the invariant factors of a matrix in rational canonical form are, because matrix in rational canonical form is this block diagonal matrix whose blocks are given by the companion matrices of these polynomials. And those polynomials are the invariant factors of that matrix in rational canonical form. So now we can say the invariant factors of an n by n matrix A are the invariant factors of its rational canonical form. So now for any matrix, even one that doesn't look block diagonal or no companion matrices in sight, you can first find the matrix in rational canonical form that it's similar to, then take its invariant factors. All right, so a theorem that follows directly from this is that if A and B are n by n matrices over F, they are similar if and only if they have the same invariant factors. Why is that true? Similarity is an equivalence relation. So A is similar to its rational canonical form. B is similar to its rational canonical form. A and B are similar if and only if these rational canonical form matrices are similar to each other. But for matrices in rational canonical form to be similar to each other, they're actually equal to each other. These are determined by their invariant factors. So these two matrices are similar if and only if they're equal, if and only if they have the same invariant factors.